All right, let's go ahead and kick this thing off. So welcome everyone to session 4 of our Graph Gurus TigerGraph 101. Today we'll be going over querying, writing queries, all the different parts of queries, the great things that queries can do, and hopefully you'll be able to write your own queries by the end of this. Firstly, there's a links document with all of the helpful links for this presentation that you can find. I'll just put this link in the chat actually for everyone to easily access it. It has been shared out otherwise, but here is that. And that will give you access to this PowerPoint and all of the other material that we'll be using for this as well. Quick housekeeping stuff. Once again, this is being recorded. And if you would like to ask a question, please do so through the Q&A tab. We'll be keeping an eye on it over the course of the presentation, and I will try to answer any questions as they come up. So let's just jump into things. What is the goal of this today? Today, we are going to learn how to write GSQL queries, but I think a little bit more importantly than that, we're going to learn how to understand a GSQL query that's already been written. So it's one thing, of course, to be able to write queries. I want you to be able to write queries, but as I was going through this just such a complex language that really to get all the way in depth into everything that I wanted to be able to show you, it's just a little bit more than we can squeeze into an hour. And as past sessions have shown, I'm not really the best at squeezing everything into the time frame. So we're going to go over a lot of the core concepts and the things that you might not normally make sense on first visit. We're going to try and tackle all of those types of things so that way you can just jump right into writing queries. And I'm going to show off as well the TigerGraph GSQL graph algorithms library. So this is a big library of a bunch of pre-written graph algorithms in query form that you can use to do things like closeness detection. There are things for page rank, label propagation, and all sorts of other algorithms that you would normally use within a graph context, and they're already written out as GSQL queries that you can go through. And obviously something like this looks very intimidating right now, but my goal is by the end of this hour, this should be something that you should be able to step through and understand exactly what the heck all of these things mean. So that's a big task, so let's just jump right into it. First, I want to say that within TigerGraph, there are two different types of queries. There is an installed query and an interpreted query. So an installed query is exactly what it sounds like. It is a query that has been installed on the TigerGraph server. When you install a query, it is compiled, it is optimized, a REST endpoint is created for you, so that way you can access that query from wherever on the web. But the process does take about a minute or two to complete. So if you're trying to rapidly iterate, develop a new query, and you're constantly trying things out, changing things and stuff like that, it can be a pain to have to wait that minute or two every time you want to change something in that query. So to help with that, there are interpreted queries. Interpreted queries basically just run immediately. So you can start writing your query and you can just run it without having to wait for that compile and install. So that allows you to sort of have that faster query iteration time of being able to develop the query quicker. But there are some drawbacks with limited functionality. There are some things that you just cannot do with an interpreted query. And if you want to do those, then you will have to first install that query. So let's just take a quick look at what that looks like. So this is just the simplest query you can possibly write, just a hello world. And here it's just shown as both a installed query or a query that you would install. So just create query, and then you give it a query name. You specify the graph that it's for, provide that graph name, and then you have a print statement. Within these queries, your print statement is what will be returned in the JSON output of the query. So there's a print statement, which will print something in the JSON output of the query. There's also a return statement. We're not going to get into that too much because that's a little bit beyond what we'll be doing, but the return statement is used if you are calling a query from within another query. That return value will be returned to the higher level query. So that's just something that can confuse people right off the bat. Is print is what you want if you want to see the output from that query. Return is really only used if that query is being called from within another query and you need to return that value up to the upper level query. You'll see that these two lines are pretty much the same, except for this create down here with our interpreted query, it is just interpret. So that's very simple. Another thing to note here is that when you create a query, it is saved onto the TigerGraph server. When you interpret a query, it is not saved onto the TigerGraph server. That query only exists for the amount of time that it is being run. And then after that, you would have to interpret it again if you wanted to call it again. But we'll get to what that looks like in code, and we'll show off, I guess, a little bit about what that looks like. So for this, we're going to be referencing our good old workbook again. This is from that GitHub repo, which is again linked out in that link sheet. There have been quite a few changes, so make sure you pull the most recent version of this repository if you want to follow along. I've broken out the different sessions into their own files now, so that should be much easier to follow along with, as well as updated the one from last session, which had a small typo in it, which caused our schema not to be created. But that's all set up now, and the graph that we'll be working off of is actually the same graph that we've been using this whole time. So it's that patents graph that we spun up in the last session, and we'll just be connecting again to that server. So we're just going to go in here. We're going to use TigerGraph to do all of this functionality from Python. But like I said, everything that you can do to TigerGraph is done via REST endpoints. So any of our other connectors, or if you wanted to do this all directly from a REST request, you could do this as well. It's just obviously a little bit easier when you have something like a pre-built connector, which handles some of the functionality for you. So just while we're establishing our connection, what we can take a look at is what creating a query looks like in GSQL. So we're again using our connection.gsql block. So we're saying with our TigerGraph connection, run this block of GSQL. And then here is a similar line that we saw before, create query name, we're going to call it sample query, and for graph patents. Patents is the name of the graph that we've been working with. And all this is going to do is print hello world. So if we were to run this, I'm not going to run it because I've already run it, but what it would do is it would create the query. That would go very quickly. And then this line down here would install the query. So that again is that process that will take a minute or two. That's why I'm not going to do it, but you'll have to trust me here that if I were to do that, and then we were to go back over to our TigerGraph solution. So this is our patents graph, and we were to go into write queries, we would see now that that sample query appears on our TigerGraph solution. And additionally, we can see this arrow next to it, indicating that it is installed versus a query that has otherwise just been saved. So anything, once again, that we're doing through this notebook, through code here, can be done through the GSQL interface here. Personally, I generally write queries through this interface just because we have the code highlighting, we have the auto suggestion within Graph Studio. We're still working on getting that into external editors, but for now, it really only exists in Graph Studio. So I find that very helpful, especially if I'm trying to do things that I haven't done before, for it to kind of give me that helping hand as I'm writing my queries. And to run this query, we can just click this run button up here, and we will see the output in JSON down here. So one thing to note is that in our output here, our JSON, the key of our JSON is typically the name of the variable that we're printing. So if we were printing a variable, it would have that variable name as our key, and then the value would be the value of the variable. When we're printing a string, however, there is no variable, so it's just going to assume the name or that string that we have as the key as well. So here it will look a little messy because our key is the same string that we're printing. But one of the ways that we can go around that, or something that we can do, and to show off our interpreted queries, is on our output here, when we have a print, so print hello world, I can specify this as statement here, which says instead of printing, hello world colon hello world, I can now say print output colon hello world. And this is also going to run an interpreted query, and we'll see that if we just run this, we get that output immediately because this is an interpreted query. And TigerGraph has a built-in function for running an interpreted query. Run interpreted query, and then you otherwise just specify your query within the body of that function. And that will allow us to do that. So now we have, once again, this is pretty much the same as our hello world from before, just as output, And we can see now that instead of having our literal string as the key to our JSON, we now have the word output because we've set it like that. So this is really the simplest query you can write, and it's not actually doing anything. It's just printing a line. It's not navigating our graph or doing anything of any of our fancy graph stuff. So in order to do that, we need a select statement. And this bit on the right is every process that goes on throughout the select statement. We're actually going to walk through this over the course of this presentation. So this may seem pretty intimidating right now, but hopefully by the end of this, you will have a complete understanding of exactly what this does and how that affects the output of the query. Basically, the select statement contains multiple clauses. So that's each one of these: for clause, sample clause, where clause. And all of those clauses kind of dictate different ways in which the query is able to traverse the graph. And additionally, the select statement utilizes patterns. So these are graph patterns to describe how it's going to navigate the graph. And we'll get into that, like I said, but let's start off with the simplest select statement that we can have. And that is selecting a vertex set. So one thing to note here is that all select statements operate on vertex sets. So that means that you need to feed a vertex set into the select statement. If you have a collection of vertices that is not within a vertex set, you will need to convert it into a vertex set. Again, we're going to cover this a little bit further on, but it's just something I really want to make the distinction of right now, is that there is a reason these are all labeled vertex set, and it's because select only functions on vertex sets. So how does this work? So first we have our result, which is what we'll be printing. So this is the resulting vertex set, and that's more or less just a variable that's created from the select statement, and that's what we're assigning the output of the select statement to. So in this example, we call it result. And then we set it equal to the output of the select statement, and here we are just selecting S. Obviously, this doesn't really mean much right now because we don't know what S is or anything like that, but for a basic select statement, you're going to have output equals select, and then what you are actually selecting. Our further clauses will dictate what that S is. For example, our from clause here allows us to specify that S is actually a vertex from within a starting vertex set. So the from statement basically says what we are selecting. And right now, in this format, it doesn't look that helpful. We're selecting a vertex from a starting vertex set. But once we get into that pattern matching with our graph traversals, you'll really start to see the power behind this. So one thing to note here as well is this S. So this we're going to call an alias within this query. And what each alias represents is an individual vertex or edge from within its existing vertex set or edge set. This will all make a little bit sense more, but just know that we are going to feed in a vertex set, and our alias represents each individual vertex or edge within that set. And to show that, so to create a vertex set, this is kind of important. We've been talking about how these select statements need vertex sets. We need to operate on a vertex set. So what exactly is a vertex set and how do we make one? And a vertex set is, first of all, it is a set, meaning it can only contain unique values. So if we have a bunch of vertices, there will not be any duplicates within a vertex set. And additionally, that vertex set can then be created by specifying a vertex type that we want to start from, and then an operation of how many or of what type we would like to select. In this case, we are going to create a vertex set called start that is going to consist of every single vertex of type application that is in our graph. So that's what this applications, that's what that means. And then dot star is just saying everything within the graph. So start is going to be a vertex set containing every single application vertex that exists in our graph. Now, it doesn't sound too important right now, but once we go to actually put that into a query, we can now see what that looks like. So this is a very basic sample query where we're going to create a vertex set called start that will contain all of the inventors within our graph. So every single vertex of type inventor. And then we are going to select every single vertex from within that set. And we're going to put that into the result of our select statement. So in this case, the select statement will iterate over each individual occurrence of the inventor vertex within this starting vertex set. And for each occurrence of that vertex, it's going to get put into this result vertex set. So now you're probably looking at that and saying, why can't I just use this vertex set instead of having to go through the result? And the answer is you can, but a basic select like this really serves no purpose other than I just need to educate you on how these select statements work. And where we really get into things is with our pattern matching. So we'll start to see now that the pattern here specifies we start at a source vertex set, and then we have this configuration here. We have this dash, space, open and close parentheses, and then within that, we name an edge type and an edge alias, and then after that, we provide a destination vertex type. So this will be a little bit easier to understand with actual vertices that are in our graph. So if you remember from before, start is all of our inventors. And then we are going to traverse the filed applications edge, because remember it's within these parentheses, so it's our edge. So we're going to traverse the filed applications edge to an application vertex. So just to put that out again, we're starting at an inventor, we are traversing through the filed application edge, and we are ending up on an application. So for every inventor, we are going to parse over all of the edges that are of type filed application connected to them and retrieve any of the applications that are connected to the other end of those edges. And something else to note here is that specifying these edge types and edge aliases is not necessary. So something to note, because our graph schema, we go back to our schema here. And one handy thing is if you are writing your queries within Graph Studio, there's this handy button down here to view your schema while you're writing your query. It can be very useful. So if we take a look at this, we started an inventor and we traverse through a filed application edge and we end up at an application. That's what that pattern was describing that we were just looking at. And if we go back to our notebook here, we can see what that looks like as well. So, sorry, I just go a little too far there. But anyway, by doing that, we can see once again, inventor, filed application, application edge. And this is going to go through for each instance. So we'll look at what that looks like within an actual query. So what this query will do, what we want to do here, is we want to select A. A corresponds to our application vertices. And we're going to select A where it is connected via an edge to our starting vertex set, which is inventors. So essentially, we're starting with all inventors. We're looking at any edges where they connect to an application vertex. And we are then taking those application vertices and putting them as our result set. And if you'll note here, I did not specify the edge that we're using. And that's because, going back to our schema, there is only one edge that connects inventor to application. So if you don't specify it, it will just use what's there. If there were multiple edges, then yes, I would need to specify to make sure that we're traversing the correct edge between inventor and application. But because there's only one edge there, I don't need to specify what edge type to traverse because there is only one edge type. So this also, when blank, will act as a wildcard. So if we had something like city that has multiple edges connected to it with multiple different names, then running that select statement would retrieve any of these types of vertices on the end of those edges, unless, like with this query, we specifically stated that we wanted a vertex of a certain type. So these can be more or less left open. So I could do file application and get rid of application there. And that would be essentially the same because there is only that one edge. Well, let's take a look at just running this, and we'll probably do the rest of this from within the notebook, just so we can run those queries and see what their actual results look like. Okay, we don't get into that until the where clause, but what this would do is print all of our applications, essentially, that are connected to an inventor, which would hopefully be all of our applications if our data is correct. But we want to get a little bit more in depth than that. Obviously, just traversing those edges isn't the best thing. So we want to be able to then filter on those things and dynamically select different things from the graph. And that's where our where clause comes in. So the where clause allows us to only select things that fulfill a certain condition. So in this case, we are going to head back to the notebook, and we're going to run an interpreted query where we are going to select inventors and their applications that are connected to an application, but we only care about inventors whose first name is Joseph. So what this where statement does, we look down here, we have, again, our alias. So S is our alias for our start vertices, and our start vertices are of type inventor. If we go back to our graph schema, well, we can see that inventor has first, middle, and last as attributes, which contain the first, middle, and last names of the inventor. So what I want to access is the first name of the inventor, and I want to check to see if it is equal to the string Joseph. And if it is, then this vertex, that S, will get placed into our result set. And when we print that, we will then only print inventors with the name of Joseph. So actually, I'm going to change this here. So we're actually selecting now our inventor. And if we run this query, we can see that we get an output of a list of a bunch of different inventors, and all of them have the first name of Joseph. We can see that they all have different full names because those are just their full names that we have stored in the graph, but everyone will have the first name of Joseph, and we will only return Joseph's. So now what you saw me do there, you saw me change what I was selecting. And this is one of the cool parts about these select statements. So right now, we are outputting all of our Josephs. But what if I wanted only applications that were submitted by someone named Joseph? Well, we're still traversing through all of our Josephs, all of our inventors whose first name is Joseph. And we're still getting all the applications that they're connected to. So instead of now filling my result set with S, which is our inventors, I can fill it with A, which are our applications. So now by running this, we will get a list of applications returned, and we can't see it here, but all of these applications are tied to an inventor whose first name is Joseph. We are only returning those applications that satisfy this from statement as well as this where statement. I could select it. So the only things that end up in this result set are the vertices that satisfy all of the requirements of the select statement. And another thing that we can do is, great. So yeah, so that's really just showing off how that works, selecting those applications based off of that filtering criteria from the source vertices. And this one just again shows off selecting all of our Josephs from here as well. If find variable S in current scope, if there wasn't a type, right. There we go. So there it is. So now after our, after we're now able to filter things, we can start getting into some of the really cool parts of the GSQL language, and that is the accumulators. So essentially what we have to think about when we look back at our queries is this is a big loop in a way. We're looping over all of the vertices of this particular starting vertex set. It's obviously much more complex than that. This is a massively parallel loop. All of a bunch of threads on the TigerGraph server are processing all of this information at the same time. So it kind of gets aggregated together. And our accumulators allow us to take advantage of that parallel processing and allow us to do some really cool things with those vertices as they go. So there are two main types of accumulators. There's a bunch of smaller types, but they fit into these two broad types, which are global accumulators and vertex attached accumulators. Global accumulators are accumulators that exist in the context of the query, or sorry, they exist within the context of the query, but can exist without outside of a select statement. So these can be used for something like if we wanted to, for example, count the number of inventors and applications that we have in our graph. So this query right here is going to accumulate. We have a sum accumulator. So this is one of our types of accumulators that will store an integer value. And what a sum accumulator does is every time a value is added to it, it just adds that to all of the values that have previously been added to it. So pretty simple there. And what this accumulate statement is going to do is we have, this should look familiar from before. We're going to select all of our applications where the inventor's first name is Joseph. And for each application there, we are going to add 1 to our sum accumulator. So for every single application that we touch, we are going to add a value of 1 to that sum accumulator, which will give us the total sum of applications that we've touched. Additionally, another type of accumulator that we have is a set accumulator. A set accumulator is very similar to a vertex set. It's just a set, so only unique items. And then we can specify what we want to put in it. In this case, this set accumulator is going to store vertices of type inventor. And again, within our accumulate statement, now what we're going to do is add our inventor to that set of inventors. So what this query is looking to do is to see if any Josephs have submitted more than one application. And the way that we would tell this is by checking the number of Josephs versus the number of applications. If we have more applications than we have Josephs, then we can conclude that at least one Joseph has submitted more than one application. So as part of understanding these accum statements, we need to understand how these are different, right? So if I were to just add another sum accumulator here to count up the number of Josephs, well, that wouldn't really work for this. So the thing that we have to understand about these accumulation statements, like I said, everything, it's this big for loop over each one of the vertices in our start set. But the thing about this accum is we're not just iterating over the vertices. The accum statement iterates over every edge that we touch, right? Because a Joseph, an inventor, could have more than one application that they've submitted. So if we only iterate through the inventors, if we only iterate through the number of inventors that there are, then if there's more than one edge, we're not going to capture that because we're only iterating once per inventor. So the select statement really iterates over the edges that satisfy these requirements. So that means that for each application, we will have an edge that connects it. So even if one person has submitted, say, 3 applications, we're now going to touch that inventor vertex 3 times over the course of this big loop because it has 3 edges that satisfy our requirements connected to it. So that's why when I'm doing this, we have to say for our applications, we can directly count it because each edge represents an actual application. But for our inventors, we can't just count it because we could be hitting each inventor more than once, and just summing up for each time that we hit it would not give us a correct value. So that's the point of the set accumulator, is this will only store a unique vertex of type inventor that we feed into it. So therefore, if we give it an inventor that we've already seen, someone who's submitted more than one application, they will not get added to that set twice. And then what we can do is we can just count the number of inventors that are in that set accumulator. So what we're doing down here, inventors.size, we're getting the number of inventors, unique inventors that are in that accumulator, and we're printing that out. So if we print here, we can see number of applications. So that's our sum accumulator, applications. That's the one that's just adding 1 to it. Every time we see an application, we can see that we have 30 applications. But then when we look at number of inventors, we see that we have 28 because we have inventors who have submitted more than 1 application. And if we were to just have this as another sum accumulator, then we would have 30 for both of these values. So that's just something that when you're writing these, understanding that the accumulation is per edge that satisfies the requirements of your from statement, it really helps you better understand what you're doing when you actually accumulate things, because you know now what is being touched by that accumulation statement. All this is getting a little bit sidetracked from the initial topic, which was global versus vertex attached accumulators. But what I'm saying here is that each of the accumulators in this query is a global accumulator. You can tell because it has 2 @ in front of it. Accumulators require either 2 @ for a global accumulator or 1 @ for a vertex attached accumulator. But we are able to access these global accumulators outside of the select statement. That's the main thing here. They're not connected to a vertex. So instead of having to iterate through vertices in order to get to them like a vertex attached accumulator, we can instead reference them from just the global context of our query. And this just kind of outlines a bit more the difference between global accumulators and vertex attached accumulators. Really just those global ones exist in a global context. A vertex attached accumulator is a unique instance per vertex it is attached to. And like I said, we'll get into this in a sec. Actually, let's just get into it now. So we'll take a look at what a local accumulator looks like and what we might want to use one for. So here, what we did was we counted all of our Josephs and we counted all of our applications. And we saw that at least 1 Joseph had submitted more than 1 application. Well, I want to know which Joseph submitted more than 1 application. In fact, I want to know which application each Joseph submitted. So this is something that I need to keep track of on a per vertex level, a per inventor level. I need to be able to store what application is connected to that inventor. And this is what vertex attached accumulators are actually for. So we can see again, we have a set accum, and we can see again that it is a vertex type, and this one is instead storing applications, whereas our other one was in storing inventors. But the only difference in declaring a global accumulator or a vertex attached accumulator is the number of @ in front of it. So this @applications only has 1 @ in front of it. So therefore it is a local accumulator. All I would have to do to make this a global accumulator is do that. So this is a vertex attached accumulator. And we have, again, our same select statement from our previous queries, except in our accumulate here, what we're going to do is we are going to take the current alias that we're on. So that's our current inventor, our current Joseph that we are processing. And the way these vertex attached accumulators work is they're basically just another attribute that you create that you attach to this vertex. So we're going to create this set accumulator. We're going to attach it more or less as an attribute to our inventor vertex, and we are going to add an application to that set. So like I said, set accumulator only contains unique values. This one only contains unique vertices of type application. So whenever we have a Joseph, so that's our S, we are going to add any application that they are connected to. That's our A. So for each vertex, for each edge that satisfies this statement, we are going to take the inventor, and we're going to take the application, and we're going to add the application to our set accum, which is attached to our inventor. It may sound a little complex just saying it out, but once we run this query, I think you'll be able to see what that looks like. So the results here we are printing our vertex. So this is one of our Josephs right here. And we can see that these are our three attributes that we talked about before, first, middle, and last. But now we have this additional attribute, which is our vertex attached accumulator. So that's at applications, which is our vertex attached accumulator. And we'll see that it contains the ID of an application which was tied to this Joseph. I don't see anyone on here that have more than one application, but this is cutting down what we are getting just due to the size of it. If we look at the full output and we were to scroll through it, we should be able to find, here we go. Here's a Joseph that has submitted more than one application, and each one of those application IDs was added to our at applications set accumulator, and therefore they're now present. So if we wanted to get what applications this specific Joseph has submitted, well, there they are. They're in that vertex attached accumulator. Now, what I said before was that you can only access these vertex attached accumulators from within a select statement. And that's kind of true. That's really only true because they are tied to the vertex. So your global accumulators before, it's just like a variable within your function. You can access it from anywhere. But these, you have to be able to access that S, that vertex that it's attached to, in order to access the accumulator. So that's just something to watch out for when you're doing this. And another thing is these, I believe I've mentioned this already, but these aliases are only available within the select statement. So I couldn't, I'm out of the select statement now. I couldn't say s dot applications because S doesn't exist in this context. S only exists within the context of this select statement. So therefore, if I were to access it out here, we would get an error saying that S does not exist within the statement. Actually, we're getting the error even before that we can't have a vertex attached accumulator outside of a DML block. So this select statement is a DML block, and it's not going to let us do that. So just keep that in mind when working with these vertex attached accumulators. And there are different ways that we can access them. So we just talked about the accum clause. And the main thing about the accum clause is that it iterates over every edge that satisfies the requirement. But what if I want to do something per vertex? I don't want to, for example, one of the things that we can do is delete information from our graph, right? So say I wanted to delete any of our inventors whose name is Joseph from the graph. Well, if I do that with an accum statement, the issue that we're going to run into is that the same that we had before, where if one Joseph has submitted multiple applications, we're going to hit that Joseph vertex the same number of times as they have edges connected to them. So if I'm doing something where I want to delete a Joseph, we're going to delete it for the first edge that's connected to it. And now that vertex no longer exists, and we're in this fuzzy state where we're still trying to go to the next edge that comes from that Joseph because they had more than one application connected to them, but we've already deleted that vertex. And also all of these operations are happening in parallel. So the thread that deleted it doesn't necessarily, or the thread that is looking for the next edge doesn't necessarily know that another thread has deleted it already. So we're going to run into those issues within an accum statement, just due to that parallel nature and it functioning on edges. And that's where postacum comes in. So postacum is essentially just another accumulate statement, except instead of iterating over every edge that satisfies the requirement, it iterates over every vertex in our start set. And where this comes in handy is if you want to access the value of a vertex attached accumulator. So like I said, these are all being modified in parallel in this accum statement. There really is no way to get a definitive result out of your accumulator until after the accum statement has finished, until after all those parallel threads have sort of combined their knowledge and given you a final answer for what exists in this accum statement. So if you want to access the values that are stored in that accum statement, you need to do so from a post-accum statement. Once again, it is after the accumulation has finished for each vertex that is within our selection set. We are going to iterate now over that and run this, whatever the contents of our post-accum are, on a per vertex basis rather than that per edge basis that was happening before. So let's take a look at what this one is doing. So we have, this is just to show the purpose of that. So our accum here, once again, these are both sum accumulators, both storing an int. Our accum here is adding 1 for each edge that it sees that satisfies this requirement. And our postacum is doing the same thing. We're just adding 1 to a separate sum accumulator. But because it's in the postacum, this happens on that per vertex level rather than the per edge level. So even though these are within the same select statement, we will get different answers from them because the accum inventors is going over each edge, and we know that there are 30 edges from the queries that we've run before, whereas the postacum is going over each vertex, and we'll see that we get 28 because we know that there are inventors who have submitted more than one application. So that's just kind of in query form what the difference looks like between an accum statement and a postacum statement. Realistically, they could have the same blocks of code in them, but they are going to function differently because they are working on different parts of the graph. So that's just kind of something to keep in mind there and something to know as you're working through that. Whenever you're assigning values to an accumulator, this should be done in an accum statement. Whenever you are retrieving values from an accumulator, it should be done in a post-accum statement. Next up, we have the having clause, and having is basically the same as our where clause. However, it happens after the accumulation. So if we go back up to our where clause, we can see, so postacum, great question. Yes, I do mean per vertex of the result set in your postacum. So that's what it is iterating over, per vertex in the result set. Oh, there's another question. Sorry, I missed that earlier. Do accumulators have to be initialized, or do they always set to 0 every time the query is run? That's a great question. So the only initialization you have to do is declaring that accumulator. All the accumulators have a default value. You can overwrite that. So for example, if I wanted the sum accumulator to start at 10 instead of starting at 0, I could do that. However, every time you run the query, yes, those accumulator values will be reset. Those accumulators only exist during the duration of the query. So even though we have this vertex attached accumulator, where was that? So even though we have our vertex attached accumulators, I don't know why I'm not finding that query I just ran, but either way, even though they're attached to the vertex and they print out as if they are, here we go, as if they are attributes of that vertex, if I were to run a different query, which did not have this vertex attached accumulator in it, then it would not show up in the results of that other query, because these accumulators only exist for the duration that the query is being run. As soon as the query is run, those accumulators are wiped from memory and they no longer exist. So you couldn't call this applications accumulator from another query unless you declared it in the other query as well, or as part of this query, you saved it as an attribute to the vertex. But by default, no, the accumulators are not stored across query runs, so therefore they will automatically default back to their default value every time you run the query. So this having clause, like I said, it's just like our where clause. Remember how we used where to filter based off of an attribute of one of our vertices or edges that it met a certain condition. Having does the same thing, except we can use it on accumulators. So what this one's going to do, this is again the same query that we've been running before. We have a vertex attached accumulator called applications, and for each application that an inventor has, we're going to add 1 to that. So any inventors that have just submitted one application will have 1. Any inventors that have submitted more than one application will have a value equal to the number of applications that they have submitted. And then using this having clause, I can say now that I only want to put in the result set vertices where the application's vertex attached accumulator has a value greater than 1. So remember, these accumulations, these accumulations all happen in parallel, and we have to kind of wait for that to resolve before we can then start accessing the accumulator. And if we were to look back at, I'll do it in here, if we were to look back at our big flowchart of the order that things happen in, we can see that halving happens after our accum and post-accum. So therefore, we can use the value of those accumulators in our halving statement. And running this query, we can see that we return 2 inventors who have both submitted 2 applications, and that explains our 28 and 30 difference between number of Josephs and number of applications. And here are the 2 Josephs that we have loaded in our graph right now, who are responsible for submitting more than 1 application. And we can quickly just see that with these accumulators, and then further filter that down with this halving statement. And then these last 2, I'm going to go through pretty quickly because there's cool things that we can do beyond these, but orderby essentially does exactly that. It allows us to order the results that we'll be returning. So for example, here, this is more or less the same as our previous query, except instead of having our halving clause, which would have only returned people with more than 1 application as specified here, we're instead using the order by clause. And what this is going to say is take our results, everything that we're putting in our result set, and order it by, and in this case, we're going to be using the value of our sum accum, and we're going to order it decreasing. So we're going to show the highest number first. And then additionally, we're going to use a secondary sort as well. So you saw that we had a bunch of people who had just submitted 1. So the order of them wouldn't really be in any order because they all have the same value here. So the secondary sort will say, sort them by last name ascending. So essentially, anyone who has the same number of applications, we'll just order them by their last name in alphabetical order. So if we print this out, we'll see first we'll have our 2 Josephs that have 2 applications. So those are these 2 vertices that we get returned here, this one and this one with 2 applications. And the next, we will get all of our Josephs with 1 application, and they will be ordered alphabetically by their last name. Again, we'll have to see the full output here, but you can trust me that our last names are in ascending alphabetical order as we go throughout this list. So that's really what orderby does. Depending on how you're using the output of your query, if you're just feeding it into some other Python library for data science or something like that, you probably don't care about the order. But if you're doing something like retrieving results for a website, you might care about the order that those results are turned in, because then that would dictate how you order them on the page. So any of that you can prevent having to do sort of in your middleware side or on your API server, you can instead do it within your TigerGraph query, so you just don't have to worry about it later down the line. And then limit further builds off of order by in a way, by essentially just limiting the number of things that we can return. So you don't need an order by clause to have a limit clause, but without an order by clause, all of the results are more or less in a random order. So if I say, just grab the first 3, then every time we run that query, we're going to get 3 different results, because the order, that parallelization, those threads that are happening in the accum statement, there's nothing to say that they're always going to resolve in the same order every time. So when you use a limit, it's usually a good idea to have an order by before it, so that way we know the order that we're in and we know the ones that we are selecting. So for example, here, this is the same query as before, where we are ordering our Josephs by the number of applications they've submitted and their last name in alphabetical order. But here we are only returning the top 3. We'll see that we only get 3 Josephs here. Additionally, something that we can do is this limit has a built-in offset functionality. This is extremely helpful. Once again, I was talking about web development. If you're doing pagination, you have a bunch of pages that you want to retrieve, then this offset is what you're looking for. So it will say limit 3, only grab 3, but start after the 3rd one. So running this will give us, again, 3 Josephs, but it's the next 3 after our first 3. You can see that these only have 1 application because they're not our top 2 with 2 applications, or the 3rd one down who was last name with a B. Instead, we have last name with a C, and so on. So that offset can be very handy, and you can also express that like this. Limit 3, comma 3 is the same as saying limit 3, offset 3. So just if you want to put that in a little bit cleaner format, you can do that as well. Next, we'll take a look at inputs. This is very important. So obviously, we don't just want to be querying for Joseph all the time. We want to actually be able to dynamically feed that in. And we specify the inputs to our query, just like with a function in probably whatever programming language you normally use, where it's within these parentheses where we define our query. So we can say here, we're feeding in a string. We're calling that in name. And what we're going to do here is select all of our inventors. And we are then going to only select inventors whose first name matches in name, and we're going to limit that to 3. So if we run this with Samuel up here, then we will now retrieve our top, or just 3 Samuels. And again, there's no order by clause here. So if I run this again, we're going to get different Samuels this time because there's no order by. And we could, of course, change this to anything and see the results of that as well. So that's all good, but none of this is really outside of what you could do with a traditional join in a SQL database, and you want to start seeing graphy things. So this is where we start getting into multi-hops. Multi-hops, one thing that they do require is syntax version 2. So that's something that you will have to specify here. And again, all this is listed out in the document. I'm going to be going a little bit quick through this now, but I highly recommend you read through this, as it will explain a lot of the things that I'm just not able to get to because of time constraints. But we'll specify that we're using syntax v2, which will allow us to do a multi-hop traversal. Now this looks just like our regular traversals before, but we just have more of them. And essentially what this query is doing is we're starting at a particular city. We're traversing from that city to an inventor, and then we're going from that inventor to an application. And we are selecting A, which corresponds to our application vertices. So we are going to find any applications that were submitted by an inventor who lived in our input city. So for this example, we'll use Boston as our input. We'll run that. And we will get applications tied to inventors from Boston. So that's just how we quickly do a multi-hop traversal. So we're starting at a city, and I'll just pull up the schema really quickly here so we can see exactly what that looks like. But we're starting at a city. We're going to an inventor, and then we're going from that inventor to an application. We are retrieving those applications, and then we are coming back and listing those applications as our result. So that's a multi-hop traversal. And you can really chain together as many of these as you want. If we really wanted to traverse from the far edges of our graph all the way across, we could do that in a single select statement. Additionally, then we kind of have directed traversals. So most of the edges in our graph are undirected, but if you have a directed edge, well, you can only traverse it in one direction, and you can specify that direction with an arrow here. So has parent is the edge that connects application to application and parent applications. And we say that we want to go along the direction of that edge. So that way we make sure we only grab those parent vertices. Quick question, do installed queries run faster than interpreted queries? Yes, they do. That difference for most queries, you probably won't notice running over a small data set, but once you have a large data set, it definitely does result in an performance increase when you have the query installed. So running this, what this will do is just get any application that has a parent application. So that's pretty simple, and that's not the most interesting to us. But one of the things that we can do that is really cool is dynamically repeat those patterns. So this is something, again, that's only available in syntax v2. So you will just have to specify that in your interpret or create graphs or create query statement. And what we're going to do here is this little star specifies that we are going to iterate over this edge however many times it occurs. So we're going to start at an application. We're going to traverse through the has parent edge. In v2, our arrow, which before was over here, now exists next to the actual edge declaration. So we're going to traverse that edge forward as many times as possible, as long as we keep resulting in an application vertex on the other side. And then for each time we traverse that, we're just going to count. So there's just a sum accumulator. We're going to count the number of parents in the chain for our particular starting vertex. And what we'll see is, so we're only returning 3 of them, and we're ordering them by the number of parents that they have descending. So we'll get our 3 with the most parent vertices attached to them. And that's what we see in our query output here. So this particular application has a parent that has a parent that has a parent that has a parent that goes on for 37 different iterations, all connected to it. And these other ones continue for 19 and 16 generations, so to speak, respectively. One last thing, or one quick thing to touch on, is the order of a query. We touched on this briefly when we were talking about schema design, how we were talking about how we wanted to break things off if we wanted to filter on them, because it's much quicker to filter off a smaller subset of things than it is to filter off, say, all of our applications and then filter them down to meet a specific criteria, when we could just start with that criteria and get any applications that are already connected to it. So that's what we're doing here. We want to select, we're trying to figure out which USPC class has the most applications submitted under it. So which class has the most applications that are connected to it. So we're going to start at our classes rather than our applications, because we may have applications that don't have classes. So there's no sense in counting those applications if they don't have any classes attached to them. So by counting our classes, we can guarantee that our classes have an application connected to them. Just because of the way that we loaded in our data, we wouldn't be able to create a class if we didn't have an application connected to it. So we know that by starting at class, we are only going to ever touch applications that have a class connected to them, and therefore have a more efficient query than having to start with all of the applications and then test them for this to see if they fit this pattern. And then any that don't, we'll have to ignore them, but we still had to process them. So by this, we just don't process any of the vertices that don't fit our requirement. And again, doing this, we'll just get our expected results. We'll see that class 424 has 471 applications, and we can see that listed out for each one of these classes. So this is where we'll kind of get into some real graphy stuff. We're going to put together everything we've worked on, and this is the average time to complete an application. And we'll look at our schema really quickly just for this. But as of now, the core of everything that we're going to learn has been established. The core of what you need to write a query is there. So we're just going to start putting that together in some of our more advanced graph queries. So each application has an event code, has multiple event codes corresponding to each event that occurred in that application's lifecycle. But importantly, the edges that connect them have the date time that that event occurred on. So what we are going to do is, for each application, we are going to traverse every edge that connects it to an event code. From each one of those edges, we're going to capture the date time that that event code happened on. We're going to find the minimum date time, so that would be the first date, and we're going to find the maximum date time, which would be the most recent date, and we're going to essentially subtract them from each other and figure out what the time difference was between our first event code and our last event code, effectively telling us how long this patent was going through the process. Now, we have some cool accumulators we can use for that. Miniccum and maxaccum do. They store the minimum value and the maximum value respectively. So our minimum accumulator will only store the minimum value that it has seen, that has been passed through it. The maximum will only store the maximum value that has been passed through it. Similarly, average accumulator here, who can guess what that does? It just takes an average of everything that's put into it. So we're going to use these in order to first traverse from all of our start sets, so those are our applications, through a has code edge to our event code. Now here you can see that I actually specified the edge type and the edge, mainly because I wanted to add this alias to it. You technically don't need to do that. I could do this and still use that alias later on in the query, like I am. But just for the sake of making this query easier to read for someone who's coming in who might not know the graph schema, they can already know that we are only traversing this has code edge. And for the duration of this query or of this select statement, we'll be referring to it by the E alias. So the first thing in our accum statement is we add the date to our respective min and max accumulators. So remember, they will only store the minimum or maximum value that they have seen. So we can just feel free to pump as many values through it as possible. And because they're vertex attached accumulators, they're only going to store that on a per vertex context. So if they were global accumulators, then we would just have the first date that any event was submitted on and the most recent date that any event from any application was submitted on. But we care about this on a per application context, which is why we are using those vertex attached accumulators. Next, we have our post-accum statement. Remember that our accum statement is happening at parallel, so we don't necessarily know the final value of this accumulator yet. So we have to wait until the post-accum before we can reference that and try to pull the value from it. And in our post-accum here, we just declare a variable, which is equal to the difference in these date times. So we have a nice built-in function with TigerGraph that will compare date times and return the number of seconds between those two dates. So we're going to take our last date and our first date from our accumulator for our specific application vertex, subtract them, get the number of seconds, divide that by the number of seconds in a day. And then what we're going to have now is this duration value for our vertex, which is going to be the number of days over which it was, the number of days between that first event and that last event. And additionally, we have a global average here that's just going to keep track of, on average, over all of our applications, how long does this process take? Let's run this query just so we can see some results. And again, in the results here, something that I'm doing, so this is actually a really cool functionality. When we ran these queries before, we got a lot of information we didn't really care about. I mean, it's important, those are the attributes of our vertex, but for this query, we didn't really care about all of those attributes. So with this bracket down here, what we're able to say is print our result set, but really only print the result dot at duration, which is that accumulator that created. So all we're going to get here is per vertex, we'll get the vertex ID and some vertex information about it, but the only attribute that we're printing is that duration. So we can see here that these applications had very long durations, but on average, applications take 812 days to process of the ones that we've loaded in. So no, once again, I am going over time, so I'm just gonna kind of wrap this up. There's plenty more here to explore, especially around how to use some of this, but this is the core of everything that you need. This is how to use accumulators. This is how to read basic queries, how to understand what these curly braces mean, and converting things into vertex sets. That gets a little bit more into it in this section. I definitely recommend checking that out, just because understanding how to convert things into a vertex set is very important if you want to then feed them into a select statement. But at the core of it, that is everything you need to know to be able to write your first queries in TigerGraph, and hopefully everything that you need to know to be able to start jumping around in something like our query library and understanding some of these graph algorithms as well. So we can start to see now that here we have our accumulators. These are global accumulators, and we can see what we are doing to them within our different select statements and how we're interfacing with those case. So there are a lot of features within GSQL that are similar across any other programming language, like case statements, which are the same as switch statements, and so on, if statements for each statement. So really, I just wanted to provide you the tools to know what might be different from what you're used to, but otherwise, please do check out our great documentation where we have a lot more information about what exactly everything does for each part of the query and how you can use all of the different data types and functions that are built in to further enhance your queries. So thank you all for sitting through that. Do you have to specify every hop in a multi-hop traversal? I love this question. So no, you don't. I'll go through this really quickly just because it's kind of neat. In a way, yes, you need to define the path that it's going to follow, but you can shorten that. For example, where is it? Here. So this is a multi-hop starting from a vertex X, going through edge called E2 to a vertex Y, through an edge to another vertex, through another edge, and finally to a vertex U. So there's 1, 2, 3 edges that are being traversed here in a line, and 4 vertices that are being touched. If there's only vertices or edges of this type between them, then you can just specify this by saying, start at this vertex, go through these 3 edges, and result at this vertex. You don't need to declare every vertex type in between. You can just say, these edges, go through them, and give me the resulting vertex. So this is handy when you don't particularly care about any of the aliases in here. So if I didn't care about what the value of the Z vertex was, then I don't need to store that as an alias and I don't need to capture it. So therefore, I just don't have to do that. If I did care about what Z was, then I would need to be able to give it an alias, and therefore I would have to write my from statement like this, where I explicitly give Z an alias, so that way I can access it later on in my select statement. Additionally, you're not just limited to one edge type per traversal. So if I had something where there were multiple edge types, like from city that we had before, I could say, I want to traverse in city or in code, and then result at whatever type of vertex results there. And you can look at that. That is, again, defined in our documentation. Very quick experiment. How do you do error checking / review of the results? So I guess by error checking, if you mean while like writing the queries, I do that all through Graph Studio. This will give me a nice, easy output here, where if I screw something up, you know, I'll get a squiggly line telling me that I did something wrong. So when I'm writing queries, typically I do them through here just for that feedback that I get. But I assume you're probably meaning something about the results. How do you verify the results? In those, you would do through, I mean, you need to have knowledge of your data there to be able to do that. You know, you need to understand your data to understand what your queries are doing, to be able to say, you know, verify if the outputs that you're getting are what you actually want. For example, I had this query that we didn't quite get to, but what this does is I was looking at inventor attorney pairings. So if we go back to our schema again, we can remember that we have inventors who submit applications, and those applications are reviewed by attorneys. So I wanted to see if there was any correlation, if there are any inventors who frequently get paired up with the same attorney when they submit their applications. You know, is there some sort of bias or something that could be going on there? I don't know. So I wrote this query to essentially, for each inventor, it counts the attorney, or for each inventor, it finds all the attorneys that they've interfaced with by going through their applications, and it gives a count of how many times they've interfaced with that attorney. Now, all of these resulted in 1, so I didn't know if I wrote this query poorly and it wasn't actually adding to this integer value when I was doing this plus equals, or if just each inventor has only ever interfaced with an attorney once. I don't know if that's part of the process. So that's one of those things where I would need to better understand my data, and I would need to take a look into my data to verify that these are the expected results that I'm getting out of my query, to ensure that my query is functioning properly. I mean, you're going to have this with any function or any code that you write. You know, you need to have an understanding of what you're doing to be able to verify that your output is correct. But I hope that this answers your question. So yeah, that was a lot of talking, definitely starting to push my limits of how far over time I can be taking these things, but I thank you everyone for sitting through this. I highly recommend you go through this workbook, because it has a lot more information than I was able to cover in this time, and it really gets into a lot of the details of how everything works and the little gotchas that you'll run into your first time writing queries, those things that'll kind of stump you. Really tried to cover those to make sure you're not going to hit any hiccups as you go through this process. So thank you everyone for putting up with me, for going over time and everything. And I hope that you were able to learn something. You now have all the tools required to set up, build your own graph and begin querying it and getting information out of it. So I really hope to see some graph projects in the future. And again, thank you all for attending.